All right, guys. So this is hopefully the only lecture that we will have to do in this new format. So the format will be as follows. I'm just recording myself doing some karaoke over the slides. So you have time for going over all the recording and pause and think about it. If there is anything unclear, then you can just write me an email. And I will wait a little bit to answer the email because there might be very common questions. So I might maybe write some notes online addressing all the most common questions. So today we are going to finish what we started last time. So this is the lecture about linear regression, convexity, and gradients. I'm going to do a recap of what we did last time so that at least this video is as self-contained as possible. Okay. All right, so we said that in deep learning we deal with the parametric models or parameterized models. And in particular in deep learning, these models have many parameters. So in the order of millions or hundreds of millions of parameters. And these models take the name of deep neural networks. So we have some input data. So in this case, this is one data point, which is one image in this example. And over here, we will have something called the deep neural network. So this deep neural network is just modeling some possibly very nonlinear function f, and this function f is parameterized by parameters theta. So we have that for this data point, this image called x, the deep neural network returns some output called y. Okay, so and in particular, we will see that this deep neural network take the form of some kind of composition of multiple simpler blocks. So here we have one particular composition, and each block will have some predefined structure. For example, one block might be modeling a linear map, and this predefined structure is left to the design of who writes the deep neural network. So usually, this is not something that we solve for. This is something that we fix when we design the deep neural network. So we fix the structure in terms of composition of blocks, and we also design the structure of each individual block. And each block depends on a set of unknown parameters, theta. So the collection of the parameters of all the blocks will be the parameters of the entire deep neural network. Okay, and what we need to do, well, we usually have access to a few data points x and a few data points y. So these will be our training pairs of examples. And our task will be to solve for the parameters theta. So the parameters that define these compositions of blocks. And finding the values for the parameters is done via a procedure called training. So when we train a neural network, we're actually solving for these parameters theta that define the function f. Okay, and how do we solve for these parameters? Well, we need to define some energy function, some cost that we need to minimize. So we're going to have to look for parameters that make some specific energy very small. And this energy is what we usually call a loss function. So this is specific terminology for deep learning. And as we will see, minimizing the loss function, or actually more clearly finding the parameters that minimize the loss function, will be done by doing some kind of optimization procedure, and usually this optimization will be phrased in terms of certain gradients. So it will involve computing derivatives of functions, and this process of computing derivatives of all the functions involved in the network, this is called backpropagation. So this was just a glimpse into neural networks. This is what expects us. And today we're going to see a very simple model. So we start simple, and then we will add sophistication as we go through. So we have seen a few examples of parameterized or parametric models. So we had a look at a linear model. So each point, let me remind you, each point you see here is a data point. So the entire thing you see here is a data set. So we have seen a linear model or a quadratic model or a sinusoidal model with a linear correction. And for each of these cases, we have that the model depends on the definition of two parameters. And actually, we need to look for the values, the specific values of A and B that make sense, that actually fit the data. So in this example, the data would be the pairs of points, X and Y. So here we use X and Y. We represent them, well, we interpret them as coordinates, so that each data point has associated to it a value for X and a value for Y, and we're looking for A and B. Similarly for these other models. Okay, so a couple of words on the notation. So this model would be a linear model, and it depends on two parameters, A and B, and we're going to write down the parameters as a subscript of the function f. And more in general, since we will not have just two parameters, we will have a set of 1,000,000 parameters, and we are going to call them theta of f. So we will write f depending on theta. And you see that I'm using theta of f here, theta of g, and theta of h, just to remind ourselves that each model has its own set of parameters, of course. So the parameters a and b over here do not necessarily make sense as parameters for this other model. And from a technical standpoint, when we do learning, we are actually looking for the optimal values of these parameters. So the problem will be to determine these values. Okay, so the simplest non-trivial case for a learning model is going to be a linear model. So we will call this a linear regression problem. We will see why. So we are given some data points. We assume that these data points come from some linear process. And so this is something that we fix ourselves. This is not something that is told us, that somebody told us. So we're going to decide that for this data, the model that makes the most sense is the linear one. It is obviously not the only possible choice. We could even decide that this is a portion of some quadratic model that maybe evolves like this. But since we have access to this data, let's say that we make this guess that this is going to be linear. So we know it should follow a model, mathematical model like this one. We want to look for values A and B. And notice that I'm calling each data point, I'm denoting it by a subscript I. So we have many data points, each with a different value for I. Now, of course, we do not expect the data to fit the line exactly. There's going to be some noise, so some deviation from the line. So in theory, we do not expect this equality to hold exactly, because there will be some additive correction. This is what we call noise. But we're not going to care too much about the noise. We don't want to find the exact value for the noise. We're going to ignore it. So, and this will be clearer in one of the future lectures, because we want to avoid a phenomenon that is called overfitting. So we don't want to find the function that describes exactly all these points, right? We don't want to describe the exact case. We want to be able to generalize. So this is something that we will see. So for now, we're going to ignore the noise. So this is our first model, the linear regression model. We are given some data, xi and yi. So these are n pairs of values. The xi in particular are called the regressors. And we're going to decide that function f theta is a linear model. And we are going to ignore the noise. All right. Now, learning means finding the values for A and B, and then once we are given values for A and B, we actually can construct a mapping that, given some new input, so some new xi, we can apply the function, the learned function f, and get some new output. Okay, so this is why we do it, right? So we are not doing this because we are just curious about how these values were produced. We want to be able to produce new values whenever we're given some new input. So this is what learning is about. So we want to generalize and find the mapping. Okay, so what we want to do, we want all these equations to hold approximately, so up to some noise, for all the data points. So for all i's from 1 to n. So what we want to do, we want to choose A and B, so the parameters, that minimize some notion of error, so some deviation from the exact equality. And how we do this? Well, we measure the distance between the true value, yi, that is given to us as an example, from what our f of theta predicts for the value xi. So we want the difference between f of x and y to be as small as possible. We want the difference to be close to 0. So how do we measure this deviation? We could just take the absolute difference between f of x and y, or we could take, I don't know, the square. So the usual thing we do is we just take the square, and then we sum up these deviations over all examples. We divide by the number of examples, so we have the average, or the mean squared error, MSE. Okay, now, and we are looking for the values for parameters A and B, such that when we plug these values inside the function f, which follows the linear model, then we get the minimum possible error. And the minimum possible error will be stored inside this number epsilon. So this is called a minimization problem. And in particular, we are not really interested in the value of the error that we get. So once we know that we get the minimum possible, we don't care usually too much about the value, but instead we are more interested about the minimizer. So the values for A and B that make the error as minimum as possible. So when we solve a minimization problem, we're actually interested in determining the minimizers. And these are going to be the parameters of our network, of our learning model more in general. Now notice that we can actually remove this division by n, and we would get exactly the same minimizers. So the minimum will be different, actually. So this epsilon that you see here will be different from the epsilon that we had here. So the minimum will be different. So it will be up to some scale, but the minimizers will be the same. So this is why usually when we try to minimize the mean squared error, then we remove the 1 over n, because we're actually not interested in this value. Okay, so now if f is linear, f of theta is linear, which it is in our case, then this is also called a least squares approximation problem, and we're going to see how we solve this problem. All right. Now, what I'm doing here, I'm going to give a name, a more generic name to this MSE that you see over here. I'm gonna call it L theta xi yi. So this is maybe a weird notation, but this is something that we see frequently when we read about deep learning. So the minimization problem will be defined in terms of a generic loss function, and the loss function for us in this example would be the mean squared error. So the loss function is denoted by this L, which depends on parameters theta, and which is given as input some examples xi, yi. And notice that this is a set of pairs. So this is a set of example pairs. Okay, so the loss function for us will be this one. And we are going to minimize this loss. So we minimize this loss with respect to the parameters theta. Of course, not with respect to the data. So the data is given as input. We have it. We are wondering about the parameters. And the loss is defined on the entire data set, okay, not just on one pair of examples. So the loss goes over all, you see, over all the data points given to us. Okay, so I'm saying this because it might be misleading, because here we see only one pair, xi, yi, but by this notation what we mean is that we actually go over all i's, so over all the n pairs. Okay, and this I think is what we, let me check. Well, no, okay, so last time we also went over the convexity, so we're going to do this now. Okay, so just to recap, so we are looking at the following setting. So we are in some learning context. We are given some examples, xi's, for example, in the form of images. Each xi is an image. And then we assume that there is some function f of theta that, given this image, will give us the value yi that we are looking for. So we have access to examples of xi's and yi. We fix the structure of f, and we just need to solve for theta. How we solve for theta? Well, we define a loss function that involves the examples xi, yi, and also involves the parameters. So from examples and from the structure of the loss function, we are going to solve for theta. And linear regression would be, we fix f to be linear and the loss to be quadratic. So in particular, that mean squared error that we saw before. Okay, so this is a very particular case, and it turns out that this is probably the most simple model that we can conceive as a learning problem. Okay, so also notice that I'm using the bold symbol for x, theta, and y, and this is because I'm not assuming that each x is just one number, just a scalar number. So it could be some higher dimensional space, some point in some higher dimensional space. All right, so in the example that we started from, of course, xi and yi, these are just two numbers, a number for x, a number for y. This is just for illustration purposes. In general, these will be high dimensional vectors. So we will have a linear model in a higher dimensional space. And to remind ourselves of this, I'm going to use the bold symbol. All right. Okay, so let's do a step in a more abstract direction. Namely, let's say that we have to solve a general minimization problem. Let's forget about the mean squared error as a loss. So let's say that we're given some general loss. This would be a general minimization problem. And we want to look for the minimizer theta for this minimization problem. And I mean, solving such problems in general is a very hard task. So there is an entire research area that is concerned about solving this kind of minimization problems, and this is called optimization. This is the research area, and it turns out that how well you can do in minimizing problems or in solving minimization problems, it depends on the specific properties of L, of the function. And also, usually we might have constraints on the parameters theta. For example, we might want to solve a minimization problem of this form, but under the additional constraint that theta be strictly positive, for instance. Okay, so this would be a constrained problem if we put the constraints. But in general, in deep learning, at least the vast majority of things we will see, we will not have strict constraints on the theta. So we will be mostly dealing with unconstrained problems. But we will see that some constraints will arise at some point. So for simplicity, let's say that we don't put any constraint on the theta. So we solve a problem in this form. Okay, so there are some classes of functions L that are easy to minimize or to maximize, but here we're going to look at minimization problems. And probably the easiest set of functions in this sense would be the set of convex functions. How do we define a convex function? Well, it is defined by what is called Jensen's inequality. So any function f that satisfies this inequality is a convex function. So what does it mean for a function to be convex? Well, what we do, so let's say for simplicity that we are on the real line. So this is a usual scalar function defined on the real line. So we have 2 points on the real line, x and y. And then we have some parameter alpha going from 0 to 1. So we see that if alpha equals 0, then this combination, this is called the linear convex combination of x and y, for alpha equal to 0 will give us y, because 0 multiplies x, and then here we are left with 1 times y. If alpha equals 1, then we are left with x, because over here we will have 1 times x and 1 minus 1 times y. And for all the values in between 0 and 1, we have all the values in between x and y. So what we're looking at here is we take 2 points, x and y. We take the convex combination between x and y, and we look at the value of f on the convex combination. So it's like you set, so you have x and y. So you have these 2 points on the real line, a point over here, x, and a point over here, y. And we look at the value of f in this range. So and the value of f in this range is drawing this curve. So we have an f that does like this over a range. And then we are also looking at the convex combination of the values of f at x and y. So we have the value of f at x, which is this one, the value of f at y, which is this one, and the convex combination between this point and this point would be this segment that links the 2 points. Now, if it happens that the value of f in the convex combination, which is this thing, is always smaller than or equal to this other convex combination, then f is a convex function. So this must be true for all possible pairs of points, x and y, and of course for all alpha going from 0 to 1. So this inequality is expressing this requirement, the requirement you see drawn over here. So this holds for convex functions. Okay, now we will assume that f is not only convex but also differentiable. Differentiable meaning that we can compute the derivative of f at all points. Okay, so we don't have singularities like the function diverging, or maybe the function creating some cusps, some sharp points. Okay, so this is a differentiable function. So this will be our assumption, and this will be very important for deep learning in general, because remember that our function f in deep learning will be the loss function. It will be what we are going to minimize. Okay. Now, of course, if f is convex, if we know the notion of derivative, we see easily and intuitively that the minimizer, so the point where the value of f is minimum, will be the point where the derivative equals 0. So let's see it less intuitively, but more formally. So let us start from the definition of convex function. So this is a definition of convex function, and notice that I'm using a slightly different definition. So before we wrote alpha x plus 1 minus alpha y, and now I'm writing x plus alpha times y minus x. So this is actually equivalent. You see these two expressions, they're actually saying exactly the same thing. In particular, we can see that for alpha going from 0 to 1, if alpha is 0, we get x. If alpha is 1, we get x plus y minus x. So we get y. And for alpha going from 0 to 1, we get all the points in between x and y. Okay, so this is equivalent to this one. All right, so this is the definition of convex function. I'm going to do some algebraic manipulation. So I'm going to divide everything by alpha. So dividing by alpha, this inequality still holds. And now let's see. So we would have over here, we would have f of x. So I'm going to compute this product. So I would have f of x minus alpha f of x plus this thing, all divided by alpha. And this is the same as f of x over alpha minus f of x plus f of y. Okay, so now we can move a few things on the other side. So I'm going to move this whole portion to the left. So moving to the left, so I come to this inequality. And now what I'm going to do, I'm going to compute the limit of this ratio as alpha goes to 0. So this is the limit as alpha goes to 0. And this resembles a lot what is our definition of derivative of a function. So this would be the limit of the rate of change. This is the definition of derivative. But in order for this to be the actual definition of a derivative of f, then instead of alpha down here, we need alpha times y minus x. Because what we want to do, we want to measure the change between f of x plus delta minus f divided by delta. And our delta here will be alpha times y minus x. So what I'm going to do, I'm going to multiply this entire ratio by y minus x over y minus x. So I'm multiplying it by 1, basically. So now I have my delta here and my delta here. So this entire limit is going to be my derivative of f. And notice that this is just, so y minus x is just some scalar, right? And whenever we have a limit of some function multiplying a scalar, well, we can move the scalar out of the limit. This is one of the properties of limits. So this is why we can now write down this entire thing just as the derivative. And this multiplies the scalar y minus x. Okay, so now we reached this point, and we did so just by starting from the definition of f being a convex function. So if f is a convex function, then we can do all these algebraic manipulations and we get to this. And now what we notice is that for f being convex, this inequality holds, and this inequality on the left, we notice that this is just the first order approximation of f, the first order Taylor approximation of f at point x. So what is it? So the first order Taylor approximation is the best possible approximation of f as a linear function at a given point x. So let's say that we are looking at our function f, when now we're looking at some point x, so this the point over here, so this is the point x, f of x. Now the first order Taylor approximation will be the best possible linear approximation of the function at that point. And this would be the line that is tangent to the curve at that point. So you should try to convince yourselves that this line is expressed as this function. Okay, so you should try to draw it. So it's actually, it is very easy to see because so there is one possible confusion. One possible confusion is that I'm calling the independent variable, I'm calling it y. So the function, this is f of y. Instead, f of x is one specific value of the function, okay, in this representation over here. So if we keep in mind that y is the independent variable drawing the curve, well then the independent variable drawing the curve, drawing the line, is still y. So over here we just have some function of y and then some shift f of x. And this function of y is linear. So try to see for yourselves if this expression is actually drawing this line passing through this point. Now, what we have now is that for convex functions, this is true, meaning that for convex functions, the line is always below, so less than or equal to, it is always below the graph of the function. So this is true for convex functions. And we also see that if we impose the derivative to 0, so then this thing cancels out, right? So this thing cancels out, and we are left with this inequality, f of x less than or equal to f of y. Which means, well, what does it mean that the derivative of f is 0 at the point x? Well, it means that this line, the best possible linear approximation, is horizontally flat, right? So this flattens out, which happens exactly at the minima of the function. So for convex functions, it is true that setting the derivative to 0 identifies the minimizers of the function. So for all global minimizers of f, we have that this is true. The derivative is equal to 0. Okay, so what do we get? Well, now we have just found out that if we want to find a minimizer for a convex function, then we just need to compute the derivative and set it to 0. So we do this, and then we will look for the point x that satisfies this equality. Because this equality implies that that point x is the global minimizer of the function. So we will do this in practice in a few slides. Okay, now of course in general we don't always deal with scalar functions over R. We will have scalar functions over Rn. So it is a higher dimensional domain. In particular, let's keep in mind that our function f will be the loss function in our case, and the set of points over which we minimize is the set of parameters. So in deep learning, we have millions of parameters. So it will be very, very infrequent that n equals 1 for us. Okay, so in general, we deal with scalar functions over Rn with n super big. Okay, so for this, we need to replace the notion of derivative with some other notion, and the notion we're looking for is the notion of gradient. So the gradient can be defined in many possible ways. Let's say that one way of looking at it that doesn't involve many other notions from multivariate calculus is just to define the gradient as the vector, well, or the list of partial derivatives of f. So f depends on n variables, so not just on x, but on x1, x2 to xn. So with respect to each variable, we can define a derivative. So this is what we call a partial derivative. So if we take all the possible partial derivatives and we stack them up in a column list, then we call this the gradient of f. And the gradient of f is with respect to the variable x, which is a higher dimensional vector in this case. So usually you don't write x down here because it is obvious from this notation that gradient of f of x must be with respect to x. Well, this comes from the notation, but let's keep writing x down here just for extra clarity of what we're doing. Okay, so what does the gradient represent? Let's see. So first of all, for functions over Rn, we have the same definition as before for convexity. So a function over Rn is convex if this is true. Now the difference is that instead of just one number over here and one number over here, we actually have a vector. So we have a vector x, which is in bold, a vector y, but the inequality stays the same. So what would be the optimality condition? So before we had that the derivative must be equal to 0, and now we ask that the gradient must be equal to 0. So what does it mean that the gradient must be equal to 0? Well, it means that each of the partial derivatives, each of the n partial derivatives, must be set equal to 0. So the 0 you see here is actually a vector of zeros. And now if this is true, then it implies that at the point x, we have a global minimum for the function. So exactly the same thing as before. Okay, so this is called the global optimality condition for convex functions. Now, let's see what the gradient represents. So this is something that we hear all the time. The gradient encodes the direction of steepest ascent, so of steepest increase of the function f at the point x. Okay, so let's see what we mean. Let's start from a simple case, an almost trivial case. Let's say that we are again in the case where x is just one number. So this function is defined over the reals. In that case, the gradient will be just the derivative of f. So let's see, in 1D, we have our function. Notice that this is not a convex function anymore. The gradient is defined for any differentiable function. So in order to have some intuition of the gradient, I don't need to draw convex functions anymore. So we have some function f. Now, the gradient in this case would be the simple derivative. And the simple derivative, we said, that is defined as the difference between f of x plus delta and f of x. So we have this minus this divided by delta. And we take the limit for delta going to 0. This will be the derivative of f, or the gradient of f for one-dimensional functions. And now, so how would the derivative look like at this point? Well, it will be some scalar value, right? And this scalar value will be the number that I can add to x to make the function f increase. So it will be on the line r, it will be the direction of increase of the function. Okay, so this is why I draw it on the axis. I'm not going to draw this arrow on the function. Okay, this would be wrong. That's a different concept. That would be the intrinsic gradient of the curve. Okay, so let's try not to make this confusion. So this is the gradient of the function at x. So it is a direction on the domain, and the domain is the real line. So it is the direction where I should move in order for recomputing f and getting a larger value. So this is the idea. Okay. Now, this intuition over here is very important to understand, because once we move to the high dimensional case, we are still going to look at the gradient as some direction, but instead of an arrow on the real line, it will be an arrow, for example, on the plane. So this would be a function defined on R2. So if we look at the gradient of the function, we see that at each point, for example, at this point over here would be the point 0, 0. If we look at the gradient, then it will point in the direction of the steepest increase. Now, you might ask, well, what is the direction of steepest increase at this point? So try to reason about that. Try to find an answer for yourself for this specific point. But in general, you see that at each point, for example, this point over here, if we look at the function, the value of the function, that we know that if we want to increase, probably we must go in this direction, right? So we take the function at this point, and we know that if we take the function at this point, we will get a larger value. So in this sense, the gradient points us to the direction of steepest increase of the function. Well, and from here you see that if the gradient is 0, then we get a minimum. So the minimum of the function, which is this here, is where the gradient is 0. Now be careful, because once again, this is not an example of a convex function. So try to apply the definition of convex function to some function that has this shape, right? So you want to draw curves, you want to draw segments and see if they cross the surface of the function or not. So this doesn't look like a convex function to me. But if this was a convex function, then the point where the gradient is 0 is also the point of the global minimum. Okay, and in particular, we see that all these arrows have a different length. So the length of the vector of the gradient is actually encoding how much the function increases in that direction. Okay, so now we need to define what the length is. And this we have seen in class. Well, usually at high school, this is how we learned how to measure lengths. So we have, for example, 2 points in R2. We want to measure the distance from point A to point B. So we represent these 2 points in a coordinate system. So, and the distance from this point to this point, which is its length, can be solved for by using Pythagoras' theorem. Okay, so this is just the application of Pythagoras' theorem for these 2 points. So this gives us the length of this segment. All right, so in matrix notation, we will have that each point is actually a vector of 2 with 2 coordinates. And we will write that this length can be, well, we will write using this notation, double pipe, and then a number 2 down here. Okay, so this is the distance between point A and B in the usual sense that we learned from high school. Now we should be very careful that the 2 that you see here doesn't have anything to do with the 2 that is the domain where the points are defined. Okay? So this 2 is not the size of the vectors A and B. Okay, so this is something else. So let's see what it denotes. So this 2 is actually replaceable by some other number p greater than or equal to 1. And this is not the dimension of each vector, but rather it is the power that we use when we do Pythagoras theorem. Okay, so this 2 is these 2 over here. So we can replace this 2 by a p, so we will have a different power, p, and also a different root. So instead of the square root, you would get the pth root. All right, so this is a new definition of distance. So it can be proven. So we are not going to do metric geometry in this course, but if there is a branch of mathematics called metric geometry or metric and topological spaces, defining what a distance should satisfy to be called a distance. And it can be proven that if you replace the 2 with a p, with this constraint, then you get a valid notion of distance. Okay? So this would be called an LP distance. So the usual distance that we learned with Pythagoras in high school is called the L2 distance, the usual distance that we are used to. Okay, and also, of course, you might have points which are not bidimensional points. So each of these vectors can have, I don't know, k dimensions. So instead of just summing up over 2 dimensions, we would have a sum over k dimensions. So this is the most general notion of Euclidean distance you can think of. So this is the LP distance between points in Rk. Okay, so this is it. Right. Now, this is a distance between 2 points. So if you are given 1 point, and one vector, and you're wondering about its length, well, this is just the distance of this vector from point 0, from the origin. So we have the distance from x to 0, which is equal to the length of x, and this is defined like this. Okay, so this is the L2 distance. We're just applying this formula over k dimensions between x and 0. So we have x minus 0, so it is just x. So this is the length of a vector. Well, this is the L2 norm of a vector. Okay. And if you're familiar with the notion of dot product, which I think we will use a few times, well, not too many, but we will use a few times, well, you can immediately see that this is equal to taking the dot or inner product between x and itself. So this would give us this summation over here. Okay, so we have seen together that you can actually try to draw unit balls, so balls with radius 1. In the L2 sense, it will give you the usual circle. So this light blue circle that you see here, so this is called the L2 unit ball in R2, because we are on the plane. If you do it with p equals 1, you get this other weird ball, which is like a rhomboid. And then for different values of p, you get all these other shapes. So we will have to do with L1 balls. We will see that these are connected to the notion of sparsity, and we will have to do, of course, with L2 balls, and probably with L infinity balls. So you can take this p, you can make it grow indefinitely, you get the definition of L infinity norm. This is also called the L max norm. We will see it in a few cases. All right, so let's finally do a few examples. So for convex functions f, we said that a global minimizer can be found by setting the gradient to 0. So try to do this exercise. This should be very easy. So these are some convex functions that appear in deep learning. So it is nice if we can convince ourselves that these are actually convex functions. So try to check their convexity. How do you check convexity? You apply Jensen's inequality with the definition of f being this one or this one. Okay, of course, under these constraints. Right, so let me remark that in these two examples, x is a one-dimensional vector. So this is just a scalar value. So this is just taking the absolute value of x and taking the power of p. So no high-dimensional spaces in these two examples. High-dimensional example, we have that any norm in Rn, so norm being defined as in here, so any norm for any p, so any LP norm is convex. For example, the usual L2 norm is convex. So try to check convexity of any norm. Well, start from L2 and then see that if you change 2 to any p, the property of being convex still remains. This is very important because for our f being a loss function, well, the loss function very often will be defined in terms of norms. Okay. Very good. So another example is that the maximum function is convex. Okay, so I think it's better if we do this together. I mean, at least a few steps as an example for you to solve these other three. So the max function is just a function that, given some vector, it returns the value of the maximum number across all dimensions, right? So x is composed of n dimensions, so it is a vector, an n-dimensional vector. So we're going to look for the maximum value over all dimensions. Okay, so it is the maximum over x1 to xn. All right, so we need to check convexity. How do we do this? Well, we need to write down Jensen's inequality. The left part of Jensen's inequality is this one on high-dimensional vectors. Now we're going to replace f by the definition that we gave here. Okay, so f is going to be the maximum over all dimensions of this point, the point which is alpha x plus 1 minus alpha y. This is one point. We're going to look at all its dimensions and take the maximum. This is applying the definition of f. And now you should try to see that this is true. So this is actually not very difficult to see. This is almost obvious if you think about it. So we are saying that the maximum over all dimensions of the convex combination is less than or equal to this other summation of maxima. Okay, try to do like a very simple example. I don't know, take n equals 2, for instance, and then try to set some values. I don't know, that for a point x, we have, I don't know, a point 0, 1, and then we have a point y, which is point, I don't know, 3, 7. Try to apply this formula. So you take the maximum, you find it. Then try to see what happens to these two other pieces and see that whatever the values of x and y, then it must always be that this thing is bigger than this other thing. This is very easy. It just comes from the definition of maximum. So it is extremely easy to see. So, for example, like if we just concentrate on this piece, it might you might wonder why we moved the alpha outside of the maximum. Well, if we take alpha inside as it was originally, and if we look at the maximum, well, it doesn't really matter that we have the alpha inside, because alpha multiplies all the coordinates xi. So it's not going to change who is the maximum, right? So we can just take the alpha outside, find the maximum, and then we multiply the maximum by alpha. Okay, so having the alpha inside doesn't change. And this is called homogeneity property. So the maximum is homogeneous, meaning that you can take the alpha outside. Okay, so this is also why we moved 1 minus alpha outside of this other term. Okay, so now the only thing you must check now is that you can split this maximum into these two maxima, but when you do the splitting, you don't have an equality anymore. You have less than or equal to. So try to do this. And once we reach this point, we see immediately that this is just the definition of alpha of f times x plus y minus alpha of f times y. So we get Jensen's inequality. So which means that the maximum is convex. It is extremely important that you, at all times, you keep in mind these kind of properties when you do deep learning. Okay, because sometimes you will find yourselves trying to do things that you cannot do. For example, you try to, I don't know, find a maximum or a minimum of some function by computing the gradient and setting it to 0. I mean, that is not enough if the function is not convex, right? So you want to be sure that the function is convex if you're going to do that. Some other things that you will try to do maybe is to compute gradients of functions that are not differentiable, right? So we will see, for example, that the maximum is convex, but is not differentiable. So this is something that we will have to take care of. Okay, so we start from convexity. So do this kind of exercise. Okay, very good. So let's go back finally to linear regression. We wanted to find a solution. Now we have all the tools we need to find a solution. So this is our minimization problem. So this is y minus f of x. F of x is ax plus b. Oops. All right. So this is in the general form. We have only two parameters, a and b. So our loss function goes from R2 to R. It is defined as in here. So we need to check, is this convex or not? Well, now you should be able to tell me if this is convex or not. So think of it. Let's try to see if this is convex or not. So it's very important to see that the function L is defined over R2, but R2 is not where we take the values x and y. So this R2 has a and b as the variables. So when we apply the notion of convexity, so convexity is going to be with respect to the parameters, not with respect to the data. Okay, so see if this is convex. Now, if this is convex, we can just compute the gradient and set it to 0, and then we should be able to find the parameters that globally minimize this function. Okay, so let's compute the gradient. So the gradient of the loss is going to be the gradient with respect to theta. So this is why I'm always writing it here, so that it's always clear that we have to compute derivatives with respect to a and b, not with respect to y and x. So the gradient of the loss. Now, the gradient, just like the derivative, is a linear operation. This is something we saw when we did the linear algebra recap. So go back to the linear algebra recap and see that the gradient is a linear operation. And this comes from the limit being a linear operation. So we did this in class. meaning that I can bring the gradient inside the summation. So I'm bringing the gradient inside. Now I need to compute the gradient of this thing with respect to A and B. Okay, so what are we going to do? So we are going to compute the derivative with respect to A and B, right? So first we see that this is the square of a trinomial. So for simplicity, I'm going to compute this square. So we're going to have to compute the gradient of this square, which is the gradient of this combination. This we learned how to do in high school. Well, if you don't remember the rule, you just multiply this thing by itself. So this would be the square. And notice that I'm going to remove this yi squared. Well, why? I mean, I'm going to compute the gradient of this thing. And the gradient is going to be derivatives with respect to A and B. So y squared is constant with respect to A and B. So the gradient is going to be 0. So I'm just removing this term completely because it's going to get me 0. Okay. So the gradient, we said, the gradient will be the vector of partial derivatives. So we will have the derivative with respect to A and the derivative with respect to B. So I'm going to put them one on top of the other. This is the derivative with respect to A of this expression, and this is the derivative with respect to B of this expression. Okay, so it should be very easy to see that this is correct. Well, if it's not, well, let me know and I will fix it. Okay, so we have computed the gradient of this thing. So this is the gradient. We're going to set it to 0. So, first of all, just for simplicity, I'm also, let me remark that the summation of these vectors is the same as bringing the summation over all 2 dimensions, of course. So I'm bringing the summation inside. Right, and we're going to set this thing equal to 0. Right, so here it is. So this is the gradient that we computed. And I'm going to set this gradient equal to 0, which means each dimension is going to be set equal to 0. And now we need to solve for A and B. Okay? So, and this can be done easily because these are just 2 equations. These 2 equations are linear. So you might say, well, they are not linear. There is a square over here. No. So these are linear in A and B. So remember that our variables are A and B, not X and Y. So these are 2 linear equations in A and B. And we have only 2 unknowns, A and B. Okay? So which means that we can solve this linear system. All right. I'm not going to do the calculations for you, but I'm going to show you how to do this more easily if you use matrix notation. Okay, so this matrix notation is something we must familiarize with. So try to gain confidentiality with matrix notation. I will probably write some notes for you to help in this task. So I'm going to write this expression directly by putting all these numbers into matrices and then writing down a product between matrices. Let's see. So I'm going to claim that we can write y equals x times I plus b times a plus b just by doing this operation. So let's see if it is true. So we have a matrix Y. This matrix Y contains all the yi's. So y1, yn. And then we have, so this is just 1 column. Okay? So I'm calling it a matrix, but this is just 1 column. Actually, give me a second. Well, usually if it's just 1 column, I would write a small case y. So maybe I can fix this. All right, and And then we have a second matrix. We have all the numbers x1, xn, so this is one column, and then we have a column of ones. Let's see why we need it. And then I'm writing the parameters a and b inside one two-dimensional column, ab. Right, so let's see. If I want to compute this matrix vector product, I would have the result. I would have a vector. The first element of the vector would be x1 times a plus 1 times b. So this would be ax1 plus b. And this is set equal to y1. So I wrote ax1 plus b equals y1. This is exactly what we started from when we wrote the linear equations. Now, the second element of the vector would be x2 times a plus b. And this is equal to y2. So you would see that this matrix vector product is actually realizing this axi plus b for all the elements. And this is equal to y. So this is just in one go, we are writing the equations that we want to be satisfied for all the data points, for all n data points. And also we see immediately that since we used matrix notation, and since we were able to just write a matrix vector product with respect to a and b, then this transformation must be linear. Of course, it is going to be linear in a and b, otherwise I wouldn't even be able to write down a matrix vector product. So matrix only makes sense if we have a linear map. This we saw when we did the linear algebra recap. Okay. Of course, this is not linear in x and y because there would be the bias b. So try to clarify this difference, this crucial difference in your mind. Okay, now there is something a bit confusing. The fact that deep learning frameworks usually would not write this expression as we did, which is to put the bias, inside the matrix. Instead, they would write as in here. Okay, so they would put the bias separately as a different vector. Okay. And once again, our unknowns are a and b. Okay, so they're not x and y. X and y are given, a and b are unknowns. If we look at it from here, we see it immediately. So this is given, this is all data, and ab, which is theta, this is unknown. We need to look for it. All right, so familiarize with matrix calculus. You should be able to look at this equation and immediately see that this is doing what we expect. So familiarize with matrix calculus, because when we will be implementing deep networks, we will manipulate matrices, vectors, tensors, and so on. So, as I said last time, I can do a brief presentation on some matrix manipulation tricks. So I will do it for next time. So just some simple reminders on how to do operations between matrices. Okay, now we have seen this expression. This is expressing all these equations at once. And this is also making the linearity with respect to AB evident. So now we should see that the mean squared error, which is y1 minus, so mean squared error would be this thing. So we must do this operation and then sum up over all n. This can be done just by applying our definition of L2 distance. So now we have this vector, then we have this vector, x times theta. So we can just take the difference between the two vectors and then take the L2 norm of the resulting vector. And we are also taking it square. So if we don't put this square over here, then the L2 norm would have a square root, right? So, but our definition of mean squared error doesn't have a square root. So I'm going to take the square of the norm to remove the square root. So try to see if this works for you. Now, this is a relation that we gave before. We said, so let's go back to that slide. See, so we said that writing down the L2 norm of some vector x is the same as taking the square root of x transpose itself, right? So what we do now, so we have the squared norm, squared L2 norm of this vector, which is the same as taking this vector transpose itself. So without the square root, because we have a square here. So we can compute this product. So computing this product is the same as taking y transpose y minus y transpose x theta minus this thing transpose y plus this thing transpose this thing. So I did it for you. Do it yourselves because there is something happening. So there are two things happening. First thing, there is a 2 now over here. So try to see if this works for you. Why there is a 2 here. And the second thing is that we only have x theta and x theta, but now we have theta transpose x transpose. Where does this come from? So try to solve this very simple dilemma. Okay, so basically now we have a new expression for our loss. This is quite easy to parse, to read. Okay, now we want to take the gradient of this thing with respect to theta, of course, with respect to theta, and set it to 0. Now here I'm skipping a lot of operations, so this can be a bit scary for you. If you've never seen a differentiation of a matrix expression with respect to a vector, it is not at all clear how I went from here to here. So I will tell you how I did it. So for now, believe me that this thing is the gradient of this thing with respect to theta. Okay? And also notice that the gradient, as we said, should be a vector, right? It should be the vector that points to the direction of steepest increase, right? So, and of course, if you look at this expression, you should see that this thing is a vector. It is a two-dimensional vector, an n-dimensional vector, and this is also a vector. Let me think. I think there is a mistake here. No, okay, so this is correct. So this would be a two-dimensional vector, right? So this is a gradient with respect to theta. So this is a matrix, this is a vector, so this is a two-dimensional vector. And of course, this is a two-dimensional vector with zeros. So we will, I think I put the entire derivation here. Yes, so I mean we can check it. Okay. Now from here, from this expression, we can just bring this part to the right. So this is just summing 0 with this part. We take it to the right, and now we want to solve for theta. So solving for theta means that we need to invert this matrix x transpose x, right? So x transpose x, inverting, meaning that we bring it to the right side. So we solve for theta. Okay, so this is how we do it in matrix notation. So we don't actually need to do any algebraic manipulation. I mean, looking at it from this point of view, it might look very confusing. I mean, solve for A and B, this is boring, we have summations, this is going to be a mess. But instead, if we know how to manipulate matrices, and in particular, if we know how to do gradients, this gradient over here, then it becomes just a simple manipulation of matrices, and we can solve for theta just by computing this thing. Okay? Now notice that this X transpose X is a very small matrix, right? So X is n by 2. So X transpose is 2 by n. So this would be 2 by n times n by 2. So this matrix is 2 by 2. So we need to invert a 2 by 2 matrix, very small. Okay. And actually, since we can solve for theta just by doing this computation, then this is what we call a closed form solution to our problem. There is nothing to optimize. There is not like an iterative algorithm that we need to go through. You just get a closed form solution. You do one calculation, get the solution. Okay? All right, so basically what we have seen that we can solve linear regression just by doing one calculation. Okay? So we find the optimal parameters A and B just by solving this, by doing this calculation. Okay, so let's see what we did with the gradient. In the previous slide, I did this magic step. So I wanted to take this thing, take the gradient with respect to theta, and then I obtained this thing. So how did I do it? Well, first of all, of course, whatever I did is gonna have to be exactly the same as doing the element by element computation that we saw before, slide 16. But instead I did it directly in matrix form, because if you know how to do it, everything becomes much easier and much to do and much easier to read as well. How did I do it? Okay, I will show you an example, and then you should try to see that this implication works. Well, not this implication. The application of the gradient to this thing actually gives this thing. So you should do this by yourself. So, example, very simple. This is a scalar function f defined with respect to parameters theta. And let's say that it's defined like this. So this is just one example of a scalar function. So first of all, you should see that this function is quadratic in theta. Try to write down this as in terms of summations. So this will be quadratic in theta, meaning that theta will appear to the square power. So we will have to compute the gradient of this. This is called a quadratic form. And since we're computing derivatives of something that is quadratic in theta, we can already anticipate that the derivative will be something that is linear in theta. Because the derivation or differentiation brings down the order of polynomials. So I'm doing this for you. So theta transpose A theta, I'm writing it by expanding the vectors and the matrices. So this is theta transpose, this is theta, and this is matrix A. Now I'm going to write for you these in terms of summations, right? So what does it mean? I mean, you need to do the product between this vector and this matrix. You would have, as a result, a vector, a row vector, and then you have the resulting row vector times a column vector. And the result will be one value, one scalar value. Okay? So, and this is equivalent as doing this operation. You see that there is a double summation because at some point we need to go over through the entire matrix. And you see that there is theta appearing in by multiplying itself. So it's going to be quadratic in theta. All right, so now we just wrote exactly the same thing as here. So we wrote the gradient of the double summation instead of writing the gradient of these bold symbols. So what does it mean to do the gradient of the double summation? Well, it means that we're going to take the partial derivatives of this expression with respect to each theta. So we have the partial derivatives with respect to theta 1, blah, 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 the partial derivatives with respect to theta n. So I just rewrote the definition of gradient. Okay? Okay, now we need to compute each of these partial derivatives, one by one. First, the one with respect to theta 1, and then for theta 2, theta n, and so on. And of course, we can expect that the one for theta 1 will look very similar to the one we compute for theta n. So, try to see if this works for you. So, actually, let me explain it. So, we want to compute the derivative of this expression with respect to theta 1. So, the derivative is linear. So, I can bring the derivation, the differentiation operation, I can bring it inside. And we see that, the derivative is with respect to theta 1. So, if theta 1 does not appear, so for example, whenever I and j are different from theta 1, then the derivative will be 0, because this term will be constant with respect to theta 1. So we will have something that is not 0 only if I equals 1 or j equals 1. And of course, it might be that both of them are equal to 1. So if I equals 1 and j is different, then the derivative will be a1j times theta j, right? The derivative with respect to theta 1. Similarly, if j equals 1 and I is something else. So we get to this solution. Okay? So this is the derivative with respect to theta 1, and this is with respect to theta n. So try to do it yourself to see if it works. And from here we see immediately that this summation, first of all, these are summing over the same indices. So j is going from 1 to n. I is going from 1 to n. So we can bring together these two summations. So I going from 1 to n. Okay, so we are just bringing together the two sums. Okay? And now we see that if we just take the theta and we put it inside a vector, then this operation is exactly the same as doing this operation. So we take A, matrix A, so these are elements for matrix A, we sum it to itself transposed, and we multiply it by theta. So this is the same as this. So try to see it. Okay, so we are done. We are done. So now we have seen that the gradient of f with respect to theta is this. So it's A plus A transpose times theta. So we see that the gradient of a quadratic function is linear. So exactly what we expect from the calculus that we have all studied. Now in particular, of course, if A is a symmetric matrix, then it means that A is the same as A transpose. So if A is a symmetric matrix, this becomes 2A theta. One example of a symmetric matrix is X transpose X. So for example, if you take the transpose of X transpose X, you still get X transpose X. So it means that X transpose X is symmetric. And X transpose X is exactly the A matrix that appears in our problem. See? Here we have theta transpose X transpose X theta. So we are exactly in this setting. Theta transpose A theta, where A is symmetric. So you see that this piece, when I compute the gradient of this piece over here, I get 2 times X transpose X theta. It is 2 times A theta. the gradient of this piece with respect to theta is 0, because this is constant. So it doesn't appear over here at all. So the only thing that remains to be done, and you should do it by yourselves, is the gradient of this thing with respect to theta. So this is something that is linear in theta, so it should be intuitive that whatever we get will be something that is constant in theta. Now, try to see why the result is exactly this thing. Good. Now, one thing that you should do whenever you do calculations, for example, of gradients of matrix functions, then you should check the dimensions if they work. Right? So we have seen before that x transpose x is a 2 by 2 matrix. So this whole thing is a 2 by 1 vector. And x transpose is a 2 by n matrix, and y is an n by 1. So this whole thing is also a 2 by 1 vector. So the dimensions are consistent. So this is, at least from the point of view of dimensions, this is correct. Sometimes when we do these calculations, then if something is broken in our derivations, then we see it immediately because dimensions do not match. So this is an easy check that you can always do. Okay, so almost done. Of course, when we do linear regression, so all these derivations that we've seen, see, so they come from the simple setting where we are in one dimension. So each point x is just one number, and each point y is just one number. But if you're doing linear regression in a high dimensional space, then each x will be a high dimensional vector, each y will be a high dimensional vector. Okay, so we definitely don't want to deal with the high dimensional case by looking at equations, because it's going to be a mess. So definitely we want to deal with high dimensional cases by using matrix notation. So when we do deep learning, we will always be dealing with high dimensional cases. So we will always be dealing with matrix notation, in particular with tensor notation, as we will see during the coding sessions and the tutorials. Okay, so let's see. For the high dimensional case, okay, so in general case, we have a setting of this form. So we have a linear model. So axi plus b equals y. The unknowns are a and b, but the data are k-dimensional points, xi and yi. So we have many such equations, but for all these equations, xi and yi change, but a and b stay the same. So exactly the linear model that we started from, but in high dimensions. So we need to solve for a and b. So let's try to write all of these equations together at once as just one matrix vector product. There you go. So it seems complicated. This is actually exactly the same thing as before. So we take all the data points xi, so we have x1, x2, and so on. We put them as columns of a matrix x, x1, x2, and so on. We do the same thing for y. We do y1, y2, and so on. So we get y. Now we're going to write this x transpose. So each point is gonna be a row. So we have x1, x2, x3, and so on. So we do the x transpose, and we also put a column of ones over here. So this is actually wrong. This is not just x transpose. It will be x transpose composed with a vector of ones. So I'm going to fix this in the slides. And over here, we are actually going to write y transpose. So how do you see that this is x transpose and this is y transpose? Well, for each data point, if we don't transpose it, each data point has d dimensions, well, actually k dimensions. So we will have x11, x1 dimension 2, x1 dimension 3, blah, 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 until x1 dimension k. So if we transpose it, we will have the dimensions moving horizontally. So we have x1 dimension 1, x1 dimension 2, until x1 dimension d. So this d should be this k. So similarly over here. So we have y transpose, x transpose, and a 1. And now we have our matrix A. I'm going to compose matrix A together with B. I'm just going to transpose B and putting it below A. So I get this matrix. There is A, and then there is B below. Now, if we try to do the calculations, well, if we try to do this matrix-matrix product, we would have to compute this row times this column, right? So this row times this column will give us this value. Now, the first row times the second column will give us the second value, and so on, right? So the first row times the last column will give us this value over here. So, and this is summarized in this expression below. And we see that if you actually do these products, so these are just summations over all dimensions, so we get this expression, right? Notice that when we do this vector times this vector, the 1 will multiply the b1. So this is why we put 1s over here, so that we can just sum b1 when we do the entire product. Okay? All right, so according to this expression, we get this equality. All right? So and this is an equality for each of the I vectors. Okay, so what I'm expressing here is just reproducing this row. So this row is reproduced as this expression, which is the multilinear regression model. Well, it is actually a linear regression model in high dimensions. So multilinear regression would be something different. Okay, now the MSE is very similar to before. So before we had y minus x theta. We're going to replace this y with the big Y, and this theta is going to be replaced with this matrix A with the B vector down here. So y minus x theta. Okay, this is an exercise for you. See that this expression, when we take the L2 norm, is the same as doing this calculation. What is TR? TR is the trace operation. TR of a given matrix is just summing all the values on the diagonal of that matrix. Okay? So TR of Y transpose Y will be a one value, one scalar, that completely ignores the element off diagonal of Y transpose Y and just takes the elements on diagonal of Y transpose Y and sums them up. So this is going to be a scalar value. Similarly, scalar value, so we get the loss. Okay, so your exercise is see that this equality is true. Try to derive it yourselves. Very good. Now, this is not, well, none of the exercises are mandatory, but if you solve not trivial exercises, you will get extra points. So you can try to solve this equality and then compute the gradient of this with respect to theta, set it to 0. If you show me that you get this, well, you should show me, of course, all the derivations, then you will get an extra point. Okay. All right, so the bottom line is that we get a very similar expression to what we got before. So we just can compute the value of all the parameters in closed form solution. We just take the data matrices, so we have the data for y, the data for x, they come in pairs, right? We do this composition, we get the solution. This solution is minimizing the mean squared error, and this is a global minimizer, okay? Okay, so to recap, we have seen a very simple model of learning. So we have this is the general setting, and we have seen that the simplest possible model is when f is linear and L is quadratic. So L being quadratic means that we are taking the mean squared error. And we have seen that in this very simple case, we can solve for theta, so we can do the learning, we can do the training, we can just solve it in closed form. So we get a closed form solution for theta. So there is nothing sophisticated behind it. Of course, we will see much more complicated cases in which f theta is not linear. It can be super sophisticated or super messy, and there we will not have in general closed form solutions. And we will also see, when we will talk about underfitting and overfitting, that the more examples xi and yi we have, then the better solution we will find for theta. Well, better means that we can rely upon the solution more. If I only show you 2 examples, then if you fit a line through those 2 examples, due to the noise, the line is not necessarily the true one. So the more observations you have, the more, which means the more examples you have, the more you can trust the solution that you find. Okay, so in general, we want to have a lot of data. Okay, right. So when we do deep learning, we will almost never have just a simple linear model. I mean, we don't even talk about deep learning. We just talk about linear regression. But we will see linear models showing up. Actually, we will see a lot of linear operations showing up. And usually, these linear operations will be a block, so a piece of a deep neural network. So many of these blocks will be linear blocks. Okay? Of course, all the blocks you see here, they will not, if they're linear, they will not operate directly on X. Right? X enters, it is processed by other blocks, then at some point it gets transformed as it goes through, and it reaches the linear block. So we will have a linear block which is not taking xi as data, but something else. So we will see it as we do deep neural networks. All right, so if we want to understand deep neural networks, we must understand all the pieces that they are composed of. So make sure you understand this linear model very well. So please send us, or send me questions, any questions that you might have, any questions that cannot be immediately answered by reading the slides and listening to the explanation. Okay, so try to think and reason by yourselves at the best of your possibilities, and then when you cannot find an answer, ask me, and I will try to reply via email or write the frequently asked questions online. And for the next time, we are going to do a coding session. So we are considering how to do it. Probably we will put a notebook online on the website with some more extensive explanations given in the notebook. The notebook will contain exercises, and I'm also going to prepare a few notes, and probably I will comment on those notes by recording a video, just as I did, for the matrix manipulation part. Okay. Also, there is some suggested reading. If you want to read more about convexity and optimality, I usually take this book as a reference. This is called Convex Optimizations, and in particular, you can read these 2 sections. This should cover what we did today. And this book is free for download. by the authors. So this is, I put a link, direct link to the PDF here. All right.